All right, AUB students, let's talk PHYS 210 finals. Welcome to your essential drill session. We're going to run through the quick strategies, the core concepts, and yeah, those common tricks the exam loves to throw at you. So let's just jump right in.
Okay, first up, we're diving into drill number 1, mechanics and energy. Look, this is the absolute bedrock of the course, right? You're guaranteed to see these topics on the final. If you can master this stuff, you're building a super strong foundation for all the tougher questions to come.
All right, let's start with a classic trap. This looks so simple, but it's designed to check if you're really paying attention to the definitions. The sign, positive or negative, is absolutely everything here. So let's break it down.
So, the key is all about direction. The block is moving up, but which way is gravity pulling? It's pulling down. Since the force and the motion are in opposite directions, the work done by gravity has to be negative. It's almost like gravity is fighting the lift, trying to remove energy from the object as it goes up.
Now, turning point problems, I know they can look kind of intimidating with all the weird functions and graphs, but honestly, they are just a test of one single core idea, the conservation of energy. Let me show you how to cut right through the noise.
And here's the beautiful, simple trick. At a turning point, the particle, well, it turns, which means for a split second, it has to stop moving. And if it's not moving, its kinetic energy is zero. So at that exact moment, the total energy of the system is all potential energy. All you have to do is set the total energy equal to the potential energy function and solve for x. It's just algebra.
Okay, this slide is huge. This is a mistake I see students make all the time. When you pull something at an upward angle, you're not just pulling it forward, you're also lifting it a little. This means the surface doesn't have to push up as hard, so the normal force gets smaller. And since friction depends directly on the normal force, less normal force means less friction. It's a really neat trick to remember.
All right, we've handled solid blocks. Let's switch gears and dive into drill number 2, fluid mechanics. We're going to see how those same principles of energy and forces apply to things like liquids and gases when they're on the move.
Here's a great conceptual question. They're not trying to get you to use a complicated formula here. They just want to see if you can apply a fundamental principle to a real-world problem. So you've got more water going in than coming out. What do you think is going on?
The key is just not to overthink it. This is a straight-up application of mass conservation. If 40 liters go in and only 24 come out, the other 16 had to go somewhere. They didn't just vanish. The most logical explanation? The pipe's got a leak. It really is that simple.
Here's another fantastic conceptual check, this time on one of the most famous ideas in all of physics, the Bernoulli effect. You've probably seen this demonstration before, but do you really remember the physics behind why it works? Let's do a quick refresh. And this table just lays it out perfectly. When you blow that air between the balloons, you're creating a channel of fast-moving air. And Bernoulli's principle tells us that where fluid speed is high, the pressure is low. So now you've got low pressure between the balloons and higher, normal pressure on the outsides. That pressure difference creates a force that pushes the balloons together. Pretty cool, right? Now, for any calculation problem involving fluids, please remember this two-step process. If you jump straight to Bernoulli's equation, you'll often have too many unknowns to solve it. You almost always need to use the continuity equation first to find the velocity at your second point. Once you have that, then you plug it into Bernoulli's equation to solve for the pressure or the height. It's a recipe for success.
Okay, let's get into our third drill, thermodynamics. This is a massive part of the PHYS 210 final, covering everything from heat engines and refrigerators to the fundamental laws that govern energy itself.
This is the absolute starting point for any problem that involves a cycle, whether it's an engine or anything else. If you get this one concept right, the rest of the problem becomes so much easier. So, what do you think? What's the change in internal energy for one full loop?
The answer is 0. It's as simple as that. If the system goes through a whole cycle and ends up exactly where it started, then its state hasn't changed, so its internal energy hasn't changed. And if the change in internal energy is 0, the first law of thermodynamics tells us that the net heat you put in must equal the net work the system does. And on a PV diagram, that net work is just the area inside the loop. It's a beautiful link between geometry and physics.
I absolutely love this quote. It's a little dramatic, sure, but it's a fantastic way to remember the second law of thermodynamics and the whole concept of entropy. It's not that the universe is really out to get you, but it definitely has a preference for things getting messy. Let's see what that means.
What this really means is that in any real-world process, the total amount of disorder in the universe, its entropy, is always going up. Think about your bedroom. It's way easier for it to get messy than for you to clean it, right? There are just so many more ways for things to be disordered than ordered. The universe is the same way. Every real process pushes it a little more toward chaos. It's a pretty profound idea.
Okay, let's zoom out. Knowing the physics is one thing, but having the right strategy on exam day is what separates a good score from a truly great one. So think of this as our final huddle before the big game. This is your coach's playbook for success.
This isn't just a list of tips. This is your game plan for every single problem on that exam. Before you even start writing down equations, run through this mental checklist. Define your system, double-check your signs, draw a quick diagram, identify the process, list what you know. I promise you, taking those few seconds will save you from so many careless mistakes and will help you find the right path to the solution every single time.
You've put in the work all semester. You know this stuff. Now you have the tactical playbook to back it all up. Go into that exam with confidence. Use these strategies and show them what you know. You've got this. Good luck.